So just now I've been over the mechanics, basics of normal reaction forces, and now I'm going to look at a slightly different scenario, and I've got my own understanding to it. I hope it's correct, but knowing myself, it's most likely not correct. But that's okay, to be honest, because even if I have like a misunderstanding in science, I think it's okay because I just have to get over A levels. After A levels, I'll get in touch with the real science, and hopefully, my all my misunderstandings right now are going to be enough for me to like pass my A levels and at least get a B in everything. At this point, I don't have high expectations for myself, but anyways. So, let me just recall what I said for the previous video. So, I clarified about the three forces right here actually being. I think the most important part is understanding like the normal reaction pair over here. And knowing that although I have drawn three forces in the entire diagram, when we actually look at the forces, we only look at, let's say, the forces that are playing with the balance are these two, and these two are like a normal reaction pair. Oh, I mean action reaction pair. Sorry if I keep saying that wrongly. And this is just like a constant force of a ball that will exert on anything, despite no matter what. And honestly, I'm still a bit sketchy on this, but like, it's okay. Just I think my explanation is okay enough. And now let's say we have like, let me explain this setting. This is our new setup. Let's just say that I have a balance right here. Let's say like a digital balance. We can read like the reading right here. This is a balance. Again, yeah, and it was a balance here, and now it's still a balance here, the blue one. And this is a magnet. So this is something new. And on top of that, I'll add something new as well. This is a wire. A wire with... Currently, there's no current going through. There could be a current. So let's say there can be a current on or off, depending on my power supply. And by the way, this circle that I've just drawn, this is like a should I say a vertical view? I'm not sure how to call it, but like, just imagine you have like a wire. Wait, no, wrong thing. Like a wire that's like a cylindrical thing, right? This is like the cross section of the wire. Just imagine it that way. And let's say if I connect it to a power supply, the current will be going into the page. And obviously, let me draw like a field line right here. This is the magnetic field line. Okay, and let's just quickly use our Fleming's left-hand rule. If I have a current pointing into the page, so your index finger should be no, your middle finger should be pointing into the page. And you also have a B field, or the magnetic field, pointing from north to south. So your index finger should be pointing from basically in this direction. Now, if you're doing this correctly, you have a force acting downwards. So from the magnet onto the balance. Or wait, no, should I just say from the wire onto the magnet? Okay, so let's just label this. If you're doing this correctly, there will be a force from or by the wire hold up, should I say by the wire? Because, okay, if this, oops, if this B field and current, if they makes a force, this force is gonna do one thing to the wire. So let's say originally the wire is here. Due to the force downwards, this wire is gonna move down. That's because of the force that's created. I think in this sense, I guess this force is acting on the wire instead of by the wire. So this is a force acting on the wire by the magnet. Well, if you think about it, it makes sense. Because, well, everyone knows that if you have two magnetic substances, they will attract. And let me just quickly redraw my scenario. This is our magnet, and this is our wire. But the reason that the wire will be lowered down, I'm not sure my grammar is correct. The reason that will be lowered is because that, let's just say the magnet is actually attracting this wire. So the force downwards, it's actually the force by the magnet. It's the attraction. And now guess what? The magnet also experiences a force that's actually going upwards because it's attraction, remember? So there's actually another force that's by the wire, because the wire is also attracting the magnet right now on the magnet. So this is interesting. Although I've seen people think of this like the F by magnet on wire and the F by wire on magnet, people say this is like a normal action-reaction pair, which is true, but well, maybe it's not true, but I'll talk about it later. But I like to think about it as attraction, because I think this is the most important thing right here. Attraction is doing the job more than anything else, and I just like to think of that way because it's more simpler for my brain to process. And well, actually there's more forces in play, because now we only consider the force between the wire and the magnet, but we haven't considered the balance right here properly yet. Because if you think about it, the balance will produce a reading, right? And let's say if my current is off right now, nothing is switched on, and this force originally, when it's not switched on, does not exist, how is the balance reading here? And after I switch it on, does the balance reading change in any way? And if so, how does it change? So this is what I'm going to be focused on explaining right now. So let's just say originally when there's no current flowing, I will not be bothered to draw the wire. So just imagine there's a wire, but there's no current flowing through. And originally the magnet itself, it does has an mg. There's always a weight for any object you might have. So, and this does not change. The mg does not change. So the magnet, this is the mg is the mass times gravity of the magnet, and which does not change at all, and it's always there, like I've explained, despite no matter whichever surface you're landing on, the mg doesn't change. So now, just like the scenario we talked about in like the previous video, there will be like a force acting upwards by the surface of the balance. This is N. And at the same time, I've talked about the normal reaction force, right? I mean the action reaction pair, sorry. And there will be force acting downwards. Sorry, my mispronunciation is really bad because I haven't spoken English for like a few weeks now because I'm at home and my parents are just speaking Chinese to me. But anyways, there's another N. You've already explained that. So let's give it some numerical values. Let's just say that initially this N equals to 1. This N also equals to 1. This is just a assumption, or like I'm trying to make you see like the difference of originally without current and with current. So bear with me, I'm just making up this random value. So yeah, so now we're settled. When there's no current or whatsoever, the normal reaction forces are like 1 Newton, upwards and downwards, it's the same. Okay. And now, if I switch on like the power supply, if I close the switch, now I have a current. Let me draw the wire. Wait, I already drew it. Okay, it's already here. So now I have a current now. And if I go back to what I've just drawn, right, just right here, this does mean that, first of all, I'll have like a force by the magnet on the wire that's bringing my wire downwards. At the same time, I'm gonna have like a force by the wire on the magnet that's gonna bring my magnet upwards. So without thinking of anything else, can you make a guess on what will happen to the balance reading? Well, I'll just give you like a quick spoiler. The change in like the balance reading is that the balance reading is actually going to decrease. And if we just think about it using our like common senses, it's because, well, originally there's no attraction whatsoever. This is just purely like the mg. But now, where there's like a current, this current is like, well, this wire, it's attracting the magnet upwards, and this will actually reduce our current reading. So the reading will actually be lower. Okay, let's look at the more scientific or scientific by me explanation. So now we have an additional force, like I just talked about. This is an additional force. And if we think about this again, well, the mg obviously did not change at all. But if you look at this right now, and remember this, I'll just quickly write again. This is force on, what again? On magnet, on wire, by magnet. And let me just draw like the normal reaction force of this on wire force. This is like the F. This is like F on magnet. Now, I want you to like take a close look of my two forces right here. So, okay, I'm trying to think what you should focus on. Okay, now focus on the magnet. Focus on the magnet. Let's ignore like everything else. Ignore this force. Oops. Ignore this force. Then let's just look at the magnet. So these two forces, the white one and the red, the white one and the red one. So we know that the magnet itself exerts a force onto the balance, which is its mg, like its original weight, which already had like on top here, it's the same weight. However, now due to the attraction, as I've just said, we also have a force that's acting on the magnet that's bringing the magnet upwards by the wire because of the attraction here. So now we can imagine that the magnet is like kind of lifted a little bit up because of that. And because of that, our current reading, no, our balance reading decreases. And if I bring these two forces in like a diagram like here, let's say this is surface of the balance. I had a force on magnet that's bringing the magnet a little bit upwards. We also had the original mg, which is to bring the magnet like downwards. If we like look at the resultant force of these two forces, we're gonna get like a downward force that's slightly smaller. Let's say originally, right, the N is like quite huge. But now, let's say this is the original N. Now it's probably decreased because, well, we had a force counteracting upwards. So you see, if this was the mg, this was the N. Like this is the first original scenario. But now it's a slightly different because, wait, hold on, wrong pen. The mg is still this much. However, I also have a force upwards, the attractive force. I'm too lazy to write whatsoever, so I should say attraction. This results in like a slightly smaller N force. You get what I mean? So if you look at this again, well, we'll have like a smaller N. So like the N right here, I'd say this N is like the force experienced by surface of the balance. The N experienced by the surface of the balance is now much smaller. I'll just say it's like 0.5 right now. This results in the N upwards. It'll also be like smaller. Let's say 0.5. So you see the difference? I think this is like the most important part right here. This is like the with current. So this is a change. The only change is not the mg, but the attractive force, aka the force that's acting, the force that is acting on the magnet by the wire. the attractive force. Because this force acts like upwards, it brings the magnet physically upwards by a little bit. It decreases the normal reaction force or the contact force that the magnet exerts on the balance. So hence, we now have like a normal reaction force of a smaller value for the pair. So both these forces have like a smaller value right here. And hence this is why the conclusion is the balance reading decreases. I hope you understood my explanation.